Good morning, everyone. My name is Maria Joy, and the topic for my seminar presentation is Green IoT for Smart Future. My seminar guide is Professor Nida Mpichu, Assistant Professor, Department of Electronics and Communication Engineering, SJCT, Palai. Before we dive into the details, let's have a look what will be covered in this presentation. First of all, the introduction followed by the history of IoT and Green IoT, then the overview of IoT and Green IoT, the importance of Green IoT and why does it matter, the four Green IoT hardware frameworks, the machine-to-machine, the wireless sensor network, radio frequency identification, the microcontroller units and integrated circuits, and the applications and some application nodes of Green IoT, the future directions, challenges and conclusion. Introduction. With the rapid development of science and technology, the world is becoming smart. Living in such a smart world, people will be automatically saved by smart devices. Let's take a very simple example. Using the Global Positioning System, the GPS, a person's location can be continuously uploaded to a server that instantly returns the best travel route for the person's travel destination. Thus, as one of the enablers of smart world, the Internet of Things IoT aims to connect billions of devices that interact with each other and exchange a massive amount of information. And the Green IoT targets at a sustainable smart world by reducing the energy consumption of IoT. The history of IoT and Green IoT. In the 1980s, embedded computing and pervasive computing started. In the year 1998, the term Internet of Things IoT was coined by Kevin Ashton. By the year 2000, the first IoT device was introduced, and there were advancements in sensor technology and wireless communication. In the year 2008, the first IoT architecture was presented. By the year 2010, Green IoT gained prominence as organizations recognized its potential for addressing environmental challenges. By the year 2015, most of the non-IoT platforms were launched, and by 2025, it is expected that the connected IoT devices will reach 75.44 billion and the continued evolution of Green IoT. The overview of IoT and Green IoT. The definition for IoT given by the International Telecommunication Union, Telecommunication Standardization Sector, the ITUT, can be IoT can be viewed as a global infrastructure for the information society, enabling advanced services by interconnecting things based on existing and evolving interoperable information and communication technologies. Since all the devices in the smart world are supposed to be equipped with additional sensory or communication add-ons so that they can sense the world and communicate with each other, they will require more energy. All this make Green IoT, which focuses on reducing the energy consumption of IoT, a necessity. Thus, to enable a sustainable smart world, the IoT should be characterized by energy efficiency. Why Green IoT and why does it matter? Green IoT reduces the energy consumption, provides sustainability, and makes the world smart and safe. And the reality is that it also has to make a business sense, be it in pure economical terms or from a random perspective. The time is right for Green IoT. The Harvard Business Review quotes that sustainable products are growing 2 times faster than conventional at a 28% premium in average across most demographics. Also, the companies that invest in low carbon investments enjoy an average rate of return of 27 to 80%, making it an excellent investment opportunity. Thus, the business who use green technologies are simply more attractive to consumers. Moreover, the consumers are willing to pay extra for sustainable goods. This underlines the importance and potential economic benefit of going green. And the entire life cycle of green IoT should focus on green design, green production, green utilization, and green disposal, which means that it should have a very less impact on the environment. Thus, green IoT offer energy efficient solutions, reducing the waste and emissions during manufacturing to field applications. The Green IoT Hardware Framework. Hardware-based green IoT enabling techniques can be classified into 4 groups, namely the machine-to-machine, wireless sensor networks, radio frequency identification, microcontroller units, and integrated circuits. The figure represents the Green IoT hardware framework and the energy efficient technologies for IoT, the machine-to-machine, the green machine-to-machine techniques, green WSN techniques or the wireless sensor network, the green RFID techniques, and the green MCUs and IC techniques. Machine-to-machine. Machine-to-machine technology refers to the ability of smart devices to communicate with each other and exchange data without the need for human intervention. It forms the basis of IoT and allows for the creation of smart devices that can operate and make decisions independently. The amount of energy saved for each approach relies on a number of key factors, including the specific technique being used, the type of end-to-end communication system, the device hardware and software, and the operating environment. And approaches for improving the energy efficiency of end-to-end communication are the energy efficient data transmission, power-aware scheduling, offloading computation, and energy efficient hardware. The energy efficient data transmission can again be classified as the data compression, cooperation between devices, machine learning algorithms, power control, and transmission protocols. In data compression is the most efficient technique as compressing data before its transmission can reduce the amount of energy used to transmit it. Also, a technique that compresses data more will require more energy. Hence, there should be a balance between the amount of data compressed and the energy needed. And some examples of data compression techniques are the Huffman coding and the predictive encoding. In Huffman coding, it is a lossless data compression algorithm that encodes data using a variable length prefix code based on character frequencies. It is simple to implement, it has good compression ratios, and it is a lossless compression technique. And in predictive encoding, it predicts values and encodes the difference between the predicted and the actual value. It has high compression ratio and low computational complexity. In cooperation between devices, M2M devices can collaborate in the transmission of data and share resources such as power, bandwidth, and processing capabilities to lower the energy consumption. The machine learning algorithms. It can be used to minimize data redundancy, which means that same data exists in multiple places in different format, and thus machine learning algorithms can be used to minimize the data redundancy and optimize the rate of data transmission in multi-cell networks. Power control. By carefully adjusting the transmission power of end-to-end devices, it is possible to reduce the energy requirement of data transmission. In power-aware scheduling, it is classified into two and can be summarized into 2 points. First one, downsize the energy consumption of M2 devices while still satisfying the required performance objectives. These algorithms can consider factors such as the remaining battery life, the importance of data being transmitted, and the energy efficiency of the transmission technology. And the second point is using the power saving modes, such as the sleep mode, in which the device can shut down the non-essential components to save power. The third green M2M technique is the offloading computation, which is classified into edge-based offloading, fog-based offloading, and cloud-based offloading. Offloading computation refers to the process of transferring computation-intensive tasks from M2M devices to external resources in order to reduce the energy consumption. In this process, it transfers a portion of computational task from one device to another. And so one example is the edge-based offloading, which do the processing, and the processing is moved closer to the edge of the network, like the routers, gateways, or IoT devices. It distributes the work between the local devices and the edge resources. And the energy efficient hardware. These include the green RFID, the green wireless sensor network, and the low power microprocessors, which include the green MCUs and ICs. These are the classification of energy efficient techniques for M2M communication. Wireless sensor network. Wireless sensors are devices that run on batteries and are able to detect specific events about their surroundings. And the deployment of a group of wireless sensors is referred to as a wireless sensor network. So in a wireless sensor network, one of the sensor node acts as a network coordinator and assumes the role of a base station or the head node. The base station can both control the networks in a centralized way and communicate with the end users and other networks. The energy conservation methods try to reduce energy consumption of the sensor nodes to extend the lifetime of the node and therefore the lifetime of the network. And some of the wireless technologies for IoT applications are the LoRa, Bluetooth, LP1, Wi-Fi, etc. The major energy saving mechanisms for green wireless sensor are given in figure 4. This is the classification of energy efficient techniques for wireless sensor network. It is classified as data reduction, radio optimization, sleep or wake up schemes, and energy efficient routing, and let me explain some of these. Since wireless sensors are powered by batteries and the cost of replacing or maintaining exhausted batteries is challenging, therefore it is essential to develop these energy efficient solutions to extend the battery life and reduce the replacement cost. And the first classification is data reduction. Data reduction is a way to save energy in which the volume of data to be transferred to the sink is reduced. These include the aggregation, compression, and data prediction techniques. In data aggregation, the main idea under data aggregation technique is to remove the redundancies in the received data by extracting only the useful information by using the aggregation functions such as maximum, minimum, average, etc. before forwarding the final data to the base station. In data compression, it compresses the data by minimizing the number of bits required to represent each block. The data compression in wireless sensor network can be classified into two, namely the local data compression and distributed data compression. Huffman coding and run length encoding are examples for local compression in data compression. And in distributed data compression, compressed sensing is an example which do not need any previous knowledge on data correlation. In data prediction, it predicts the part of the sensed data without any transmission, and it is divided into two: single prediction scheme and dual prediction scheme. In single prediction scheme, it is made in a single point in the network when it is more expensive to obtain a sample than to predict one. And in dual prediction scheme, clustering is used and predictions are made in channels or nodes. Radio optimization. In radio optimization, modulation optimization technique is the most efficient as it finds optimal modulation parameters to minimize the energy consumed by the radio. BPSK and QPSK are the optimal choices for long transmission distances. And in radio optimization, it comes the cooperative communication. Cooperative communication can improve the quality of the received signal and provide better energy savings and smaller end-to-end delays by creating a virtual multiple antenna environment such as MIMO, multiple input, multiple output antenna environment. And in transmission power control, it improves the energy efficiency by adjusting the transmission power of radio, and the power controlling methods can improve the network lifetime. Sleep or wake-up schemes. Turning off unused wireless resources has become a widely used method for reducing power consumption. So when a system has large sleep power compared to its active power, the system can save a large amount of energy. And among these, duty cycling approach is very energy efficient as it switches a sensor node on and off depending on network activity. Radio frequency identification. So, an RFID setup includes unique identification tags, a reader, and middleware communication. The technology uses radio frequency waves for non-line of sight communication. And in an RFID system, RFID tags act as the basis for the whole network. RFID tags can store information regarding the objects to which they are linked. And reducing the size of RFID tags should be taken into consideration to lessen the amount of non-degradable material required in their fabrication. And one promising area of research in the field of RFID is the development of passive RFID tags, which do not require an energy source and can operate indefinitely as long as they are within the range of an RFID reader. And some of the green RFID techniques are mitigate overhearing problems, avoid tag collisions, and transmission power control. Mitigate overhearing problems. When a reader initiates an interrogation of RFID tag by sending a wake-up signal to its surrounding, which results in multiple tags come out of the sleep mode. All unintended tags continue to remain in active mode until they receive a sleep command from the reader and contributes in energy consumption known as the overhearing problem. Thus, it is essential to mitigate the overhearing problems to save energy. When multiple tags come out of the sleep mode, they can result in tag collisions. And the anti-collision protocols like Aloha and Tree mitigate simultaneous tag responses in order to avoid collisions that lead to the wastage of bandwidth. In transmission power control, with the help of Berkeley MAC or the BMAC protocol under various operating conditions like variable distances between nodes, it reports energy saving up to 57%. Thus, the BMAC protocol provides a flexible interface to obtain ultra-low power operation, effective collision avoidance, and high channel utilization. Thus, these green RFID techniques can be implemented for reducing the energy consumption of IoT devices. Microcontroller units and integrated circuits. Basically, a microcontroller unit is an energy-efficient and cost-effective solution for embedded computing applications. And for improving the energy efficiency, the data processing component should only be active for brief periods during which it reads, processes, and transmits information, and the rest of the time it remains inactive, a process known as duty cycling. And the figure represents the typical power consumption pattern of a microcontroller for IoT applications. Here, the microcontroller waits for a sensor event or internal timer to wake it up when it is in a deep sleep state for the majority of the time. Upon waking, the device restores power and clock function, retrieves new data, processes it, and then returns to sleep after saving its state. The latest CMOS ICs have the capability to enhance energy efficiency by delivering required functionality. Also, ASIC application-specific integrated circuits can operate at low voltage without a decrease in its performance, which also contributes to energy saving. The applications of green IoT. With respect to IoT and green IoT, there are a lot of applications, and some application scenarios are as follows: the smart home, industrial automation, smart healthcare, smart grid, smart city, smart farming, and smart transport. The application notes or case study for green IoT. Our first example is arid agriculture, the intelligent precision farming in Israel. Israel is a country with limited water resources, yet a booming agricultural sector. There, companies in agriculture have evolved the traditional Israeli drip irrigation technology with the help of green IoT to develop precision farming. With the case in Israel, agriculture producers were up against significant challenges, and the situation there was located in an arid climate, they only had limited water resources. Moreover, since they managed vast farmlands, efficient management was a considerable challenge. Because of the scale, blanket application of pesticides and herbicides was more or less the only solution, and similar practices also impacted water usage. The result is less profitable, more wasteful, and difficult to manage operation. Thus, the situation there was an unstable output with the difficulty of managing vast farmlands. By implementing the green IoT solutions, the agricultural producers could leverage sensors and big data to better understand the conditions on a very local level, allowing them to apply the ideal amount of water, fertilizer, pesticides, and so on. Moreover, drone machine technology and greater use of sensors and monitoring enabled a much higher degree of efficient management. The result of the implementation of green IoT was higher and more predictable output, much lower use of resources such as water and fertilizer, and easier and cheaper management, perhaps most importantly, the tastier and healthier produce for everyone. Thus, by implementing the green IoT, it resulted in a greener future with a high and stable output with a reduced resource use and was easy to manage. Our second example is greener greenhouses and optimal climate control in northeast China. Greenhouses allow for a higher agricultural output. However, the harsh climate in northeast China had effects on greenhouses, making efficient greenhouse climate management a huge and costly challenge. So greenhouses usually require full control of the indoor climate and its many variables. And the situation in northeast China was extreme and ever-changing climate and weather condition, highly labor intensive to operate a greenhouse, and the inability to effectively manage greenhouse climate conditions with a lower output. By implementing the green IoT, the data-first approach helped in collecting climate and crop data with sophisticated sensors. Machine learning algorithms made climate and crop conditions more predictable. Smart operations automatically responding to changing conditions to ensure optimal output. And by implementing the green IoT, it also resulted in a green future with fully automated climate control, a high output, and highly efficient resource use. These are the advantages and disadvantages of green IoT. Our first advantage is its energy efficiency. Green IoT devices are designed to be energy efficient, which can reduce the overall energy consumption. Our second advantage is its environmental sustainability. Green IoT can help monitor and manage environmental resources. It also reduces the carbon footprint by optimizing processes and reducing waste through IoT technologies. Cost savings. Green IoT can lead to cost savings through reduced energy consumption, improved resource management, etc. And the disadvantages are initial investment, complexity, and resource consumption. The deployment of green IoT system often requires a significant upfront investment in devices, sensors, and infrastructure. Complexity. The IoT systems can be complex to implement and maintain, requiring specialized knowledge and expertise. And in resource consumption. While green IoT aims to reduce resource consumption, the maintenance of IoT devices can still contribute to resource consumption. The challenges of green IoT. The following open problems and research directions concerning green IoT are observed. More research is needed to develop a common architecture for IoT because it will help in developing more generic solutions for energy efficiency. Recyclable material for the development of sensors needs to be thoroughly investigated. Applications should be green to minimize the effects on the environment. Both devices and protocols used to communicate should be energy efficient with less power consumption. And realistic energy consumption models of different parts of IoT systems such as wireless sensor network, core network, embedded system or cloud computing, etc. are needed. Future directions for Green IoT. Green IoT will change our future and can make it greener and healthier in both economically and environmentally. The research work done recently in realizing the gap in Green IoT are mostly focusing on Green IoT services, integrated RFIDs, energy efficient models and planning and localization. Hence, researchers need to find solutions for the following fields mentioned in the figure. These are the potential future directions for green IoT. First one, the zero energy. Designing IoT devices to be powered by self-sustaining power sources such as solar, wind, or kinetic energy is an important area of research as it enables the deployment of autonomous and sustainable IoT networks. These technologies must be capable of harvesting energy from the surrounding environment and converting it into electrical energy that can be used to power the IoT device. Examples of such technology include photovoltaic cells for solar energy harvesting, piezoelectric materials for kinetic energy, and small wind turbines for wind energy harvesting. to enable IoT devices to operate without a constant power source is an important area of research as it can help to reduce and address the challenges of limited battery life and the need for constant charging or replacement. Thus, batteries and supercapacitors are the two types of energy storage solutions that can be used to power the IoT devices. The routing schemes. Smart routing schemes aims to address the challenges by utilizing real-time data and algorithms to dynamically adjust network route based on the network conditions, traffic pattern, and the energy availability. These schemes can be implemented at various levels of the network, from the sensor node to the edge devices and gateways. Adaptive AI and ML. The development of AI-based energy management systems and machine learning algorithms for IoT devices is a rapidly evolving field that can significantly improve the energy efficiency and sustainability of IoT networks. An AI-based energy management system uses machine learning algorithms to analyze the data from the IoT devices, such as usage patterns and energy consumption, to identify the opportunities for energy optimization. This system can also incorporate data from external sources such as weather conditions or energy prices to further optimize energy usage. And the fourth one is intelligent sleep mode, which include smart sleep mode, adaptive AI and ML, prediction and adjusting using power usage. Sleep mode is a power-saving state in which a device uses less power but remains operational. By developing intelligent sleep mode algorithms, IoT devices can dynamically adjust power usage based on usage patterns, network conditions, and energy available to achieve the optimal balance between power consumption and performance. Thus, intelligent sleep mode algorithms use machine learning techniques to analyze data from the device and predict usage patterns. And the last one is wireless charging, which includes the development of new technologies, integration of wireless charging into more devices, and the use of renewable energy sources. Research is ongoing to improve the energy efficiency of wireless charging, which can downscale the required energy to charge devices and decrease the environmental impact. And one approach for improving the energy efficiency of wireless charging is to optimize the power transfer between the charger and the devices being charged. This can be achieved through the use of advanced circuitry and the control algorithms that monitor and adjust the power transfer to ensure that the charging process is efficient as possible. Conclusion. IoT technology has demonstrated heightened benefits in enhancing our life quality in smart cities. In specific, we highlighted the green IoT for efficient resource and energy utilization, creating a smart world. Paving the way for smart world, the Internet of Things connect everything in the smart world. Green IoT will help reduce the greenhouse effect and further optimization of IoT greenhouse footprint will be taken care. And the green IoT has the potential to revolutionize industries, improve resource management, and contribute significantly to the global transition toward a more sustainable and environmentally friendly future. These are the references. Thank you.